A small town in southern Arizona has a declining population that follows exponential law. The population decreased from 8,000 people in 2005 to 7,200 people in 2007. We want to predict the population in 2015. So if the population is following exponential law, that means that it is decreasing. It's an exponential decay situation. So we can begin with our general model for any sort of exponential growth or decay. A is equal to a sub 0, e raised to the RT power. And so we want to go ahead and compare time, how much time has passed, and what the population is in any given year. So rather than saying that the population was 8,000 in 2005, rather than actually inputting 2005 for our t value and then 8,000 people here for our a value, we want to actually have a value here of a time equal to 0. So we're going to make a statement that we're going to let t equal 0 in the year 2005. So I'll just say that over here. Let t equal 0, in other words, letting time begin in the year 2005. And then this allows me to have a t value of 0 and a number of people of 8,000. So then when we take a look at the next set of information, which says we had 7,200 people, that's my amount, A. That was in the year 2007. Well, if t is equal to 0 in 2005, then that would be 2 years later. So when t is equal to 2, our a value is 7,200. And we want to know the population in the year 2015. So again, looking at beginning in 2005, that would be 10 years later. So ultimately, we're looking for a t value of 10, and then our question mark, we're looking for the amount, the population, when t is equal to 10. So we start off with our model, and we notice immediately that at a time 0, we have 8,000 people. That's our initial value. So that's going to be our a sub 0. So we can input that value, which will give you a is equal to 8,000 e raised to the RT power. So we still don't know the r value. We don't know our relative decay rate. So looking at our table, we have another value of t and a that we haven't used yet. We have a time of 2 and an a value of 7,200. So we'll go ahead and input 7,200 for a. We know that we have 7,200 people when t was equal to 2. So that would be 8,000 e raised to the r times 2 power. And now you have an exponential equation to solve. So you begin by isolating this exponential quantity. So we'll divide both sides by 8,000. And you want to simplify this fraction on the left-hand side. Remember, you do not want to round. So 7,200 divided by 8,000 is going to simplify to 0.9. And that's an exact decimal. If this had been a rounded decimal, we would be in trouble. So that's when you would want to store. But in this case, it's an exact decimal of 0.9 or 9/10. So we have 0.9 is equal to e raised to the r times 2 power. And now we're going to rewrite this equation in logarithmic form, remembering that right now the base is e. So in log form, it'll be log base e of 0.9, so 0.9 becomes my argument, is equal to r times 2, which I'm just rewriting as 2r. And log base e is the same as natural log. Many of you probably will skip this intermediate step, but I'll include it just so you can see what I'm doing as I rewrite the equation in log form. So we have the natural log of 0.9 is equal to 2r, and then divide by 2. So we'll have r is equal to the natural log of 0.9 divided by 2, and then you can go to your calculator for that to get an approximate, and that's about negative 0.05. Remember, pause the video so you can check these calculations on your own with your calculator. Now, a few things to remember. We're getting a negative R value, but that makes sense because our population is decreasing. It's decaying exponentially. So it should make sense that we're getting a negative value. Anytime R is negative, we have exponential decay rather than exponential growth. And because this is an approximate value, we do not want to round this number. You want to make sure that you store this value using your graphing calculator. And now you have a model for the population decay in this situation. We have A is equal to 8,000, again that initial size, times E raised to the negative 0.05 t power. This is the model that relates the number of people in any given year when t is equal to 0 in 2005. And now we want to know when t is equal to 10 what the population is. So we want to find A of 10. And again, you can use your calculator for that and check your answer against mine. I'm getting 4,723.92 if you were going to round to check your decimal and your accuracy. Of course, we can't have 0.92 of a person, so you could just say 4,723 people would be the estimate for the population, our prediction for the population in the year 2015. Now, as always, there's more than one way to approach these application problems. So let me go back to my table and let me just mention how you could also approach this problem without using the general model of A is equal to A sub 0 e to the RT. Because this model, remember, is using a base of E. And if we think about this problem as exponential decay, we don't have to use a base of E if we can figure out the base on our own. So when I say you're figuring out the base, that means you're taking a look at what your multiplier is. So numerically, looking at a table of values, we have 8,000. What are you multiplying by here? What are you multiplying by to go from 8,000 to 7,200? So again, remember to compute that, if it's not a number that pops out at you right away, we could take our amount of 7,200 and divide it by the previous amount, which was 8,000. So 7,200 divided by 8,000, which is 0.9. So my multiplier here is 0.9. I'm multiplying by 0.9. So I could use 0.9 as my base. And in fact, if I wanted to multiply again by 0.9, if you wanted to continue making this table of values, then you could multiply 7,200 times 0.9, but you would have to be aware here that my time values, of course, I was jumping by 2 years. So I'd be going to 4 if I was continuing my table. But rather than continuing the table, let's think about how to write this as an equation. So I'm going to have my initial population of 8,000 people, and this time I'm going to use a base of 0.9. Now in the past, we would have just raised it to the t power, but you're going to notice that we have a little bit of a problem here because taking a look at the values in my table here, when t is equal to 2, I want to have an output of 7,200. And if you think about what would happen here if I would input a 2, and you could just try that on your calculator right now, 8,000 times 0.9 raised to the second power, and you're going to notice that if that's the case, you're going to get 6,480 people rather than getting 7,200 people, which is what we intended. But of course, the reason that we're not getting the right value here is because my time values, I wasn't going up by ones essentially here, right? I jumped from a time of 0 to a time of 2. So to fix this, I have to adjust my exponent. I want to be able to plug in a 2, substitute in a 2, and get out a value of 7,200. So to fix that, rather than having a t here, I'm going to end up needing a 1/2 t. Watch how this adjustment will make this work. If we're taking a of 2, then we're taking 8,000 times 0.9, and now it's 1/2 times 2. So now we'll be raising that to the first power, which will now give us 7,200 like we intended. So another option, if you don't want to use E as the base and you want to think about your multiplier, what are we multiplying by? Here we're multiplying by 0.9, then we could use this as our model. And then, of course, we want to know, okay, what's happening in the year 2015, which was A of 10. So same thing as before, just inputting 10 for time. Whoa, sorry about that. That would be a 0.9 raised to the 1/2 times 10 power. And you'll see you're still going to get 4,723.92 people.